So let's pick up where we left off in class when we were doing some demonstrations of center of mass. What we're going to do is define center of mass, more specifically the equation, and primarily focus on problem solving. Before we do that, I want to just summarize some of the key points we made from the demonstration. Let me point out now, before we get too much further, the main thing I want you to take away about center of mass is that it does not change when you have only internal forces. It goes along with the idea of conservation of momentum. We will do a problem or two that illustrates this, but the other problems we're going to do show other applications, even though they're not as highly emphasized on the AP exam. All right, so let's go ahead with this. So center of mass, sometimes called center of gravity, is the point at which an extended mass, so this is some mass that is spread out in space, as all masses are, okay, it's where it's centered. Maybe a better way of putting it is located, as I was talking about in class. So if I have, let's say, a simple object like a meter stick that's this long, you could say, well, it extends from 0 to 100 centimeters all along here. But another way of saying it is, where is all that mass located? Rather than say it's all spread out, it's easy to say it's located right there in the center. We can treat that object as if all the mass is located there when we're trying to do the first law of motion, conservation of momentum, many of the dynamics that we've learned. All right, so that's the primary motivation for understanding center of mass. Okay, other points. It is the center of mass object that moves in a straight line, okay, when not acted on by an external force. This is more easily demonstrated in class, but let me just do a really crude demonstration right now, at least on the board here. So imagine I have two vehicles, right, that are tied together by some spring. Okay, this is a spring right here. Initially, they are moving this way with the speed of 2 meters per second, and it's a frictionless surface. Okay, so the first law of motion says once they get going, they got to continue moving forward with the speed of 2 meters per second. Well, let's say, all right, they've been moving along here. Let's say at this spot right there, we release them, and we know that the car on the left is going to move this way, and the car on the right is going to move to the right. Now, if they have the same mass, they'll move at the same speeds. If they have different masses, they'll move at different speeds by the law of conservation of momentum. However, we can ask what happens to the center of mass of that system. All right, now this is a very odd idea, and if it doesn't make sense, make sure you ask in class. And before we press the button to release the springs, they were moving forward at 2 meters per second. So if this represents the center of mass, and this is 2 centimeters every second, so that's what it's going to do. So when we press the button and we release the springs, those springs are internal to the system. They're not external. So the first law of motion still holds. It basically says those cars must continue moving forward at 2 centimeters per second. You might ask, well, how can that be if this car is going to be moving faster than 2 meters per second? Let's say it's moving 4 meters per second, and let's say this one is moving at negative 2 meters per second. Okay, I'm not sure if I've got the numbers worked out in terms of conservation of momentum, but that's irrelevant. But the point is, the center of mass of those two cars, they'll move in such a way that their center of mass still keeps moving forward at the original 2 centimeters per second. In other words, if you were to take a snapshot of these two cars at any given second and locate their center of mass, you would see it continually moves forward and forward and forward. So it's an interesting application of either the first law of motion or law of conservation of momentum. Secondly, it is a center of mass that moves in a parabolic arc when projected at an angle through the air. So I talked about that in class a little bit. There are some illustrations of what a wrench would do if it's twirling through the air. Its center of mass follows a parabola, or even a human who is doing a, let's say, flip, right? As they change the shape of their body and rotate faster or slower, their body still follows that arc. All right, other points. Center of mass is the point at which an object is balanced. Okay, I put a period there, and I'm going to cross out that word. Place your finger at the center of mass, and an object will not rotate. Okay, so you take any object, if there's a center of mass located on an object, and you put your support there, it's not going to tilt one way or another. And we'll see the importance of that when we get into rotational motion. When a center of mass is over a support base, Okay, like your feet when you're standing on the ground, okay, then the object will not topple. So I did some demonstrations of that. And this is just to remind you. So as soon as your center of mass moves beyond your support base, you must fall over unless you readjust your base, which is what we do when we're starting to fall over. All right, lastly, and this is really conservation of momentum, and that's how I'm going to write it here because that's the simplest way. In an explosion, even though there are many moving parts, the center of mass of the system must remain the same, especially when there are, or only when there are no external forces. Okay, so that's just another way of saying is if I have, let's say, a bomb right here that's just sitting there and then it blows into a bunch of little pieces flying in all directions, if I look at the center of mass of every single piece after the explosion at any given time, I will see that the center of mass stays right where it was. They must move in such a way to keep that. Okay, so how do we calculate this center of mass? We're going to do it for some simple shapes and mass distributions. This is not on your reference tables, but I want you to know it anyway for some problems we're going to do. So a center of mass is a position. Okay, it's not a mass. It's where you are, but I'm going to call it XCM. Okay, and it's basically, depending on the number of objects you're talking about, it's a summation. All right, it's a sum of the mass of any individual piece, I, times its position, I, all over the mass of the object. Okay, so I'll do an example in a minute, but there are three objects we want to find the center of mass of. We got to sum up the product of these on top and then divide it by the total mass on the bottom. All right, we'll see that in a minute. So, key things about applying this. X is the distance from any arbitrary 0 point. You choose what you want to call 0. The smart way to do it is, so it's convenient, and generally it's on one of the objects, and I'll show you later. X can be positive or negative depending on your choice of your origin, or your 0. Again, we'll see that illustrated in a minute. And if you have two dimensions, you have to look at an object that is spread out in x and y dimension, then you have to do the equation separately for each axis. And I may have time to do a problem like that. Okay, so let's just do some practice. Here we go. The first one is just conceptual. Let's say I have these capitalized letters that spells out physics rules. We could say pinpoint conceptually, qualitatively, where is the center of mass. So for an object or a letter like I, we know it's going to be right there in the middle. For the X, we know it's going to be right there. How about for the U? Well, the U is in 2 dimensions, right? We have a symmetry this way down the middle. My alignment is not very good, so we know it's got to be halfway between the columns, if you will, but in the X direction, it's got to be somewhere in here. So long story short, you know it's going to fall somewhere in the center of that U, closer to the bottom, and I don't know how good a result, that's a little off. Okay, it's right around there. So it's not even on the U, and you can have that. For the L, it's similar. It's going to be towards the bottom, and it's going to be towards the right, so it's going to end up right about there. Okay, again, it's not on the L. So those things, letters, where you could not balance it. So there's no way I could put my finger, if I were to lay these letters flat in my hand and were to place a finger on any part of that, there's no way I could balance it because the center of mass is not even on the letter, where it is on the I and the X. All right, so I'm going to move on from that. Next one is a more common problem. How do you find the center of mass if I have 2 lumps of mass right here along some arbitrary axis? Okay, so we know that this little m is x distance away from the vertical here, and this is 3x. So I want to find the center mass. I first have to establish what my 0 is. I can choose anywhere along here to be 0. The easiest thing is going to call this 0. There's my origin. Okay, so let's apply the equation. So my x center mass is going to be the product of this mass times this distance, so that's mx, plus, so I got to do a summation, this mass, which is 4m, times its distance, which is 3x, okay, all divided by the total mass. So that's m plus 4m. Okay, then the rest is just fractions. So this is mx plus 12mx, so that's 13mx on top, divided by 5m. The m's cancel out, and I'm left with 13/5 x. Okay, so 13/5 x is about 2.6. So look at that. It's somewhere between this guy and this guy, right? Here's x, here's another x, so it's going to be really close to the big object, which makes sense because the big object has a lot of mass, so we're not going to find the center of mass equally between these two. Okay, let's continue on here. Okay, next problem C is a little bit more difficult, but it's the same idea. What's a slight little twist to it? All right, so imagine we have a meter stick that has a mass of 63 grams. And on it I hang two masses, a 221 gram mass and a 121 gram mass. You might say those are odd numbers. Well, I want to show you this in class, so I had to be realistic for the hangers on that. Okay, so I want to find the center of mass of my system. In other words, where could I put my finger such that if I place my finger there, the whole system would be in balance? That's one way of looking at the center of mass. We expect it to be somewhere between these two masses. This is the 221 gram mass. This is the 121 gram mass. So we wouldn't necessarily expect it to be halfway between the two right here. We expect it to be skewed more towards this one. However, the twist in this one from the previous problem is we must take into account that the meter stick itself has mass. So what contributes to the center of mass? Okay, so we got three terms in our center of mass equation. So let's work that out. So I'm going to work it out up here. So we have center of mass, XCM. Okay, let's take the obvious things. Let's take this mass. So this mass has a mass of 221, and we're going to take 0 to be the left edge. And so based on this, this is 10 centimeters away, so I'm not going to worry about units. I don't have to convert to kilograms or meters. All right, plus the contribution of the smaller mass, so 121 times 60. All right, now, here is a trickier part, and I guess I've already kind of given away. What do we do with the meter stick? Well, we know its mass is 63, but how far away is it from 0? Rewrite that for a second. Okay, so this is where the concept of center of mass of the stick itself, forget about the other things, is really important. So even though the stick is extended all along here, let's treat as if all the mass is located in one spot, i.e. at the center of mass, which would be roughly halfway along the stick. So I have 49.5. I'm not sure why that comes from. There's something physical on that, on the meter stick itself. So that's how far away. So the center of mass of the stick, not the system, is right here, and that's your 49.5. Okay, and then I'm going to divide it by the mass of everything, so that's 63 plus 221 plus 121 in parentheses, and I've already done the math. I believe I have, and I get a value of about 31.1 centimeters. Okay, so like I said before, it falls here is if we had nothing hanging here, so it's going to be shifted a little bit towards the heavier mass, which makes sense. Okay, we're going to skip letter D, and actually, yeah, I'm going to skip D and E. Okay, next problems. These are ones I want you to try on your own coming into class. Number 1 and number 2. Okay, and what we'll do in class, yeah, try number 3 as well. This number has to be changed from 3.54 to 3.37. So I'll give you the answer to this one. The answer what they ask is, what must be the mass of the support rod? The mass of the support rod must be 1 kilogram. Okay, so this is saying this 10 kilogram mass is 2 meters away from 0, another 2 meters, 1 meter. You have to add in the mass of the kilogram. Now I'll give you a hint. Where is the, so this is the support rod. Where is that located? It's located at its own center of mass, which would be, if this is 5 meters long, it's 2.5 centimeters, or excuse me, 2.5 meters away. So that's the part that you may have trouble with. All right, give these a shot. Okay, come in with questions, and we'll see how things go from there.